the point I want to make, though, is if you add up the masses of those quarks, they're much less than the mass of the proton. So what's going on here? They make up the proton, and yet the proton's much heavier than its ingredients. Answer is there's another contribution to the mass, which has nothing to do with the Higgs field, which is the thing we were talking about before, the energy in the glue holding the quarks together.
Oh, the gluonic force.
There's energy holding them together equals mc squared. There's mass associated with that energy, and most of the mass of the proton is coming from the glue that's holding the quarks together.
So, why does most of what we call mass come from motion and fields, rather than from the tiny constituents themselves? Consider a proton, the workhorse of ordinary matter. Its 2 up quarks and 1 down quark have small masses, measured in a few million electron volts each, yet the proton tips the scales at about 938 MeV. The difference is not an accounting error. It's energy stored in the strong interaction, the restless kinetic energy of quarks confined to an impossibly small space, and the energy of gluon fields binding them. Einstein's relation doesn't just convert units, it asserts that energy is mass. Lattice QCD, a supercomputer approach that solves the equations of the strong force numerically, reproduces the proton's mass from first principles. Give it the quark masses and the strength of the strong force, and out comes a proton of the right heft. The lesson is stark. What seems like substance is often the inertia of a dynamic system forced, by nature's rules, to keep moving. If interactions can conjure mass, can they also take it away? Yes, and our sun proves it every day. When protons fuse into helium, the helium nucleus weighs less than the sum of the 4 protons that built it. That missing mass is released as energy, light, and neutrinos, fueling sunshine. In nuclei, binding energy is negative. It reduces total mass. Gravity plays the same game on grander scales. Assemble a planet, star, or neutron star, and the gravitational binding contributes a negative term. A freshly formed neutron star emits a blast of neutrinos carrying off on the order of 10% of the core's mass energy. What's left is a compact object whose total mass is less than the sum of its free neutrons. Meanwhile, at the proton scale, the dominant contributions are kinetic and field energies that increase the mass beyond the bare quark totals. The sign flips with the specifics. Mass is a ledger, and interaction energy can register as a deposit or a withdrawal. What sets the scale for this emergent mass in the first place? The strong force hides a remarkable feature. Its strength depends on the energy at which you probe it. At high energies or very short distances, quarks interact weakly, a property called asymptotic freedom. At lower energies, the force grows strong enough to lock quarks inside hadrons. It refuses to let them fly solo. From this running of the coupling emerges an energy scale called lambda QCD, around a few hundred MeV. That single number, arising from a dimensionless coupling, sets the size and mass pattern of the hadrons. This is dimensional transmutation. No mass parameter was put in for the force itself, yet a mass scale appears. The early universe felt this shift. In the first microseconds, quarks and gluons roamed in a hot plasma. As the cosmos cooled through the QCD scale, quarks became bound, and the familiar inventory of protons and neutrons emerged. In that cooling, the energy that once lived in free quark-gluon motion reconfigured into hadron masses, the universe minting the inertia of ordinary matter as it expanded. How does gravity read this ledger? General relativity doesn't just couple to mass, it couples to energy, momentum, and pressure, the entire stress-energy tensor. A box filled with light weighs more than an empty box, because trapped photons contribute energy and pressure, and both gravitate. Inside a star, pressure helps support the weight, but in Einstein's equations, that very pressure also acts as a source of gravity. That's why neutron stars, where pressure is extreme, are so precarious. Concentrate enough energy of any form, particles, radiation, fields, and if it's confined within its Schwarzschild radius, space-time closes off into a black hole. When black holes merge, their gravitational waves carry away energy. Detectors feel that energy as ripples, and the remnant black hole's mass is reduced by exactly that amount. Gravity doesn't ask whether the mass came from quark masses, gluon fields, or nuclear binding. It curves space-time in response to the total energy momentum content, indiscriminately and consistently. So, what are we actually weighing when we weigh ourselves, a rock or a star? We're weighing a balance of energies, the jittering of quarks and the field energy that confines them, the negative binding that holds nuclei together, the restless thermal motions, and even the pressure in extreme cases. Some of that inertia owes its existence to the Higgs field. Elementary fermions and the W and Z bosons get their masses that way, but the bulk of the mass of ordinary matter arises from the strong forces dynamics. Two mechanisms, one universe. When you pull on the idea of stuff, it unravels into relationships governed by equations, energy shaped by forces, forces that set scales, scales that emerge from running couplings, and gravity that tallies it all into weight. That perspective reframes everyday experience. The mass of your body, the stability of a mountain, the pull of a planet. These are expressions of motion and interaction disciplined by the laws of physics. Matter is not merely assembled, it is maintained. The solidity of the world is the equilibrium of ceaseless activity, and the cosmos, from the interior of a proton to the edge of a black hole, is fluent in the exchange rate between energy and mass. Like if this was interesting and hit the subscribe for more.